Right, I thought I'd show you a quick demonstration I've just set up. I'm not sure if it's going to work or not, but the idea is to show an explosion and conservation of momentum during that explosion. Now, I haven't got anything set up to actually measure if momentum is conserved, but the idea is just to see this in principle. So, what we've got here is, firstly, a trolley, which is pretty much free to move. There's quite a small amount of friction, so it approximates to being a closed system where there's no external resultant force acting. So momentum should be conserved just with this trolley on its own. If I push it and give it a certain amount of momentum, in an ideal world it would continue with the same amount of momentum forever and ever and ever, which on this runway it would not, but it's reasonably close. The other component is a gun I've just made out of an elastic band on a piece of wood, and the thing it's going to shoot is a weight, which is quite heavy. Now it turns out the weight is almost the same mass as the trolley. The trolley's got the bit of wood on it which adds to it, so the masses aren't exactly equal, but it doesn't matter. Momentum should be conserved whether the masses of the two objects are equal or not. So what's going to happen here? Well, get that bit of string out of the way. The gun is going to fire the weight off to the left, and if the weight fires off to the left and nothing else happens, then that looks like momentum is being created, because before this event happens there's currently zero momentum, total momentum before. If the weight goes shooting off to the left, then we've just created momentum, which is not allowed, because we've just said that this is a closed system with no external resultant forces acting. So the weight can't just fly off to the left. Something must move to the right to cancel that out. You remember that momentum is a vector, so if we say moving to the right is positive and moving to the left is negative, then it's entirely possible for these things to both start moving and yet the total momentum afterwards be zero, because one has positive momentum and one has negative momentum. So that's what we're expecting to see. We're expecting to see the trolley move off to the right with positive momentum, the weight move off to the left with negative momentum, and for the total momentum to be zero, which is what it is at the start. Now look, it's probably, we can't measure whether it's zero or not, but we can get a rough idea just by having a look at it. So what I'm going to do is try not to exert any external resultant forces by pushing it or pulling it or doing anything. So the way I'm going to try and release the string is by lighting a match and burning through it, so I don't actually really come into contact with the string at all. No idea if this is going to work, but we'll give it a crack. Now, is momentum going to be conserved? Is the weight going to fly that way and the trolley fly this way at roughly the same speed? Let's find out. So I'm going to try not to touch the setup at all and exert any force on it. I'm just there we go. Can't wait to see that one replayed. It certainly looked to me like the weight got fired that way and the trolley went this way. Now what we call, with guns and cannons and all sorts of things like that, these sorts of explosions, we call that recoil. When something shoots one thing one way and then the thing that's shooting it moves the other way, we call that recoil, and that occurs when anything like that happens, when any cannon fires a cannonball. If the ball flies off one way, then the cannon at least is going to try and fly off the other way, although there might be some resistive forces slowing it down so it doesn't go on forever, which would be not very advantageous. Why does all this happen anyway? Why is momentum conserved in the first place? It all comes down to Newton's third law, which says if one object pushes on another object, then that object pushes back with an equal and opposite force. And that's sort of what's going on here. So when this object here, the gun, pushed on the weight in this direction, forces can't exist on their own in isolation. So Newton's third law says forces always come in pairs, they have to. So if the gun is exerting a force this way on the weight, then the weight must be exerting a force that way on the gun, and therefore on the whole trolley thing, because they're connected together. So if a force is being exerted by the gun on the weight is exerting a force on the gun. And as we've seen, it's a very low friction situation, so if a force is applied by the weight on the gun, then the gun moves that way, and the weight accelerates this way. So it's all down to Newton's third law. I hope that's a half-decent demonstration anyway, because I couldn't really find any on YouTube. Obviously the whole calculations thing is a separate thing, which I'll do in another video, or link to one. But I just wanted to give you an actual demonstration of it in action.